So how do we actually implement this? Well, there are two ways of doing it, and they do happen to map on the two prominent software that people use, FSL and SPM. Now, SPM says, just do an OLS, just do an ordinary least squares, and that'll be just fine. And that's how you do your random effects analysis. This is also why we typically, SPM refers to its group analysis as a random effects analysis. The truth is that unless you have a real estimate of the variability across people, you can never do a real random effects analysis, but you can approximate it, which is what SPM is doing. And the idea is this: if you can assume that the variance at the first level, so the sigma squared within, are the same for all subjects, in other words, if you can assume homoscedasticity in terms of the first level variances, if the variance, if measurement error within each of your participants at the first level was kind of the same across your participants, assumption number one. Assumption number two, if the design matrices are balanced, which means if everybody had this more or less the same design, it doesn't have to be in the same order, but if everybody had the same cells in their design, so if everybody kind of saw the same conditions, then you can assume sphericity. And if you can assume sphericity, then this two-step model, this hierarchical model, this summary statistic model, is really equivalent to the all-in-one. Okay, so the idea is we can't do the all-in-one. We will do this. We will do the summary statistic approach. Under these two assumptions, under sphericity, which means under homoscedasticity and under balanced X matrices, then so under sphericity, the summary statistic and the all-in-one are identical. So it's legal for you, SPM says, it's legal for you to use the summary statistic approach, where you take the beta from the first level analysis, you carry that forward, and you do the analysis, the group analysis on those. Right. In other words, it's legal for you to calculate the group variance, right, the random variance, just by looking at the variance across the betas that you've estimated, or the contrast betas that you've estimated at the first level. Now, this is wonderful because it's a very rapid approach. It's very simple. All you have to do, you run your first level, you get the effect, you can calculate easily the variance across the effect, and then you use that as your yardstick. On the other hand, is it a good assumption that all the variance, the measurement error across your first level analysis, so for example, across your participants are the same? Well, what if you had a participant who was particularly distracted? What if you had, some participants learned a strategy, other didn't, and that injected some noise? So the variance at the first level might not meet homoscedasticity. And at the same time, are the first level matrices truly balanced? So is everybody getting the exact same cells? Most of the times, I think this is perfectly reasonable. Who knows? You could think of some designs where maybe you're doing remembered versus forgotten, and one of your participants forgot most of the trials. And so you have a lot of observations from condition A and very few observations from condition B. That would hurt this. But overall, most of the times, your participants are all getting just about the same design matrix. They're just getting trials in different orders. So the second half of it usually is met. The problem is the homoscedasticity, which is not always met. And that's why FSL does things a very different way. FSL says, no, you cannot just take the betas and carry those forward. Essentially what they say is you have to take the betas or the contrast betas and also carry forward the variance from the first level. In other words, it's not enough to do a random effect analysis. You can't just look at the variance across the effects. You can't just take the variance across those green effects that we saw earlier and use that as your yardstick If you do that, it's not the same as the all-in-one approach. They show mathematically that if you take both the beta, the group beta, and you use as your yardstick the variance across the effect, so the sigma squared between, plus the average of the sigma squared within, so if you do a mixed effects analysis, then that is mathematically identical to the all-in-one approach. So in other words, SPM kind of uses this faster approach. They say, just take the beta, calculate the variance across it, and that's your yardstick. That's your sigma squared between. FSL says, no, 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 that doesn't work. If you do that, it's not identical to the all-in-one. What you need to do is you need to estimate the betas at the first level, do the group analysis, so get your group average. Then you need both to calculate the variance in the across participants, so the sigma squared between, and you need to take the variance from the first level, the sigma squared within, and you need to sum those two. And these two together, so the mixed effects variance, that's your yardstick. And if you do this, then this is identical to doing that giant all-in-one approach, which we don't want to do because it's too computationally intensive. So this stratagem, by using the mixed effects variance, allows you to say that the two-step approach, the hierarchical, the summary statistic approach, is identical to the all-in-one approach. So you carry forward the variances from the first level, you estimate the sigma squared between, and then you perform essentially a GLS, or rather a weighted least squares. Because what you do, essentially, what you're doing is you're using the variances for each subject kind of as weights. For example, if a participant were very distracted and they would have a large sigma squared within, that would downweigh their contribution to the group analysis. So in other words, the fact that the variances within individual are included in this analysis allows you to weigh differently different participants. Hence, it's a weighted least squares, where the diagonal matrix is not just the sigma squares between, which would be all the same, right? But it's a sigma squared between the random effects plus the within subjects fixed effects. And of course, the only thing that changes along the diagonal is the sigma squared within. Again, this allows you to downweight if somebody has, is very distracted and has, a lot of variance in their measurement, that kind of downweights them. And this is what allows this two-step summary statistic approach or hierarchical approach to be identical to the all-in-one. So in other words, again, if you do a weighted least squares, if you include the within subject error at the group level, then the summary statistic approach is identical to the all-in-one, but without all the inefficiencies of having to do the giant analysis. So this is great because bad participants, those with large variance within, they'll be downweighted. So this kind of adjusts for variance in performance in your participants. Statistically, it's also valid because this is exactly identical to what we wish we could do, the all-in-one, but we don't want to do because it's too inefficient and computationally too hard to do. Of course, on the other hand, this is computationally more intensive than the simple OLS, but not a big problem. Now, over the years, it has been sort of finding all this out has been a fairly entertaining debate, mostly between the FSL people and the SPM people on how to exactly implement this approach best. And it all started with Carl Friston, really a trailblazer in the field of functional analysis of functional MRI data. And as I said earlier, his approach is just, look, assume homoscedasticity, assume that the variances, the within subject variances at the first level are, are all equal, and then do an ordinarily squares. So carry forward the betas, in other words, average them, get your average, your group effect, and as the yardstick, use the variance across betas of different participants. In other words, use the between subject variances as your yardstick. So just do an OLS this way and you'll be fine. However, a few years later, Beckman and colleagues in a wonderful paper showed that actually the summary statistic approach with only the between subjects variance is not equivalent to the all-in-one approach. So you're doing something that is not equivalent to the approach that we wish we could do, but it's just computationally too crazy, the all-in-one approach, and also very inefficient. If you want to implement in a summary statistic way something that is equivalent to the all-in-one approach, then you need to carry forward not only the beta from the first level analysis, but also the within subject variability. In other words, you need to use as your yardstick the sum of the between subjects and the within subjects variance. In other words, you need to use the sum of the within and between variance. In other words, you need to use a mixed effects approach if you want to use a summary statistic approach and make it equivalent to the all-in-one approach. And now people usually oppose to this that the within subject variance is usually so small that it doesn't matter. But in 2005, Smith, which is the creator of FSL, actually showed that at times the within subject variance can be pretty significant and pretty large. So assuming homoscedasticity doesn't make good sense. You really need to carry forward the estimated variance within subject into the group level analysis. And so Carl Friston said, look, fine. Here's what we're going to do. First, you ought to know that the OLS is actually very robust to failures to meet homoscedasticity. So the OLS is generally fairly robust to heteroscedasticity. But Carl Friston says, if you really want to feel good about it, here's what I'm going to offer you. I'm going to offer you that you carry forward the betas and you use as the yardstick, you use the between subjects effect, the between subject variance. Then for every voxel that is significant, so only for the subset of voxels that are significant compared to the random effects, we're going to go back to the first level. We're going to use a restricted maximum likelihood approach to actually estimate the within subject variance for those voxels at the first level. And then we're going to redo the group analysis only for the significant voxels with the mixed effect, so with both the between and the within. In other words, given that the mixed effects variance is always larger than just the random effects, it makes sense. You just take those that are significant compared to the random effects, add to the random variance also the within variance, and see if any voxel is still significant compared to the mixed effects. So this way you can be ensured that you are faster because you only had to do this iterative estimation for the significant voxels. But you still get the benefit that the result of this is indeed equivalent, at least in the significant voxels, is equivalent to the all-in-one approach. Finally, however, Jeanette Mumford wrote a wonderful paper in 2009 showing nonetheless that indeed the OLS is really very robust both to violations of homoscedasticity, so both to unequal variances at the first level, and even to the presence of outliers. However, this was only true for one sample t-tests. So if you're doing anything fancier than a one sample t-test, the OLS might actually not be robust to any such violations. So a GLS, or in other words, a weighted least squares, really, is typically just a statistically more appropriate path to pick.